Welcome. This is 48A video 4 and we're going to talk about significant figures. Scientists and engineers talk about measured values and we have to discuss how many decimal places we have and how long the unit should be, and we call this significant figures. It's very important to us, as I'll explain. So there's two types of value. There's a qualitative value, you could say it's hot, or there's a quantitative value, you could say it's 95 degrees C. Now the fact that I wrote down 95 degrees and not 95.0 degrees is significant, and this is why we need to worry about this, because it tells me what kind of thermometer I used to actually make that measurement. We can divide quantitative values into exacts. That is, let's count the number of balls inside that dustbin, and we'll find there's 17, not 18 or 16. There's 17. Everybody will get 17 because we're counting. Whereas for measured values, if I say measure the mass of that car, then the measured value that I get would be 2,654.3, and I got that by looking at a scale, and there was 2,654 and there was 2,655, and the needle, if you like, was pointing like there, and I said, oh, 54.3. That 0.3 is my estimate. And so what this number tells me is that the actual scale was marked in kilograms and that I estimated fractions of a kilogram. And that's the way the system works. If your scale is, if the smallest division on your scale is millimeters, you have to estimate a fraction of a millimeter. If the smallest division on your scale is in seconds, you have to estimate a fraction of a second, and so on. Okay, so I can say, when I write a measured number down, I can assume that the last digit is uncertain. We estimate that. Maybe I'll estimate a 3, maybe you'll estimate a 4. Reasonable people can disagree on that. And the earlier digit's the result of observation. We literally looked at the scale and said it's beyond the 3, it's beyond the 4, it's not to the 5, so 2, 6, 5, 4, because it's beyond the 4. No one should disagree about that. Reasonable people may disagree about the last digit, but should agree about the earlier digits. And we refer to the number of digits in a measured value as the number of significant digits. This example here, 2,654.3, has 5 significant digits, and it's useful to keep track of that. So how do we decide the number of significant digits? Well, there's certain rules we have. The left-handmost non-zero digit is the most significant. Let's say our number is 2,750.6. Then I would say, the left-handmost non-zero digit is always the most significant. Let's do another example. 276. If there is not a decimal point, the rightmost non-zero digit is always the least significant. So there's my first, that was a 6, and there's my last. And if there is a decimal point, the right-handmost digit is the least significant digit, even if it's a 0. So over here, it's whatever this is at the end, even if it's a 0. All digits between the most significant and the least significant are significant digits. So in this case, I would have 5, and in this case, I would have 3. There's also rules for truncating calculations. let's say that we multiply two numbers together or add two measured values together, then we have to have an answer that is the right number, the correct number of significant digits. And so we might say, and so the two sets of rules are, when we're multiplying and dividing, the number of significant digits in the answer equals the number of significant digits of the original number with the lowest number of significant digits. So if I have a 2 significant digit number multiplying a 3 significant digit number, my answer is a 2 significant digit number. If I have a 1 significant digit number, very imprecise, multiplying a 7 significant digit number, my answer is a 1 significant digit number. And the same goes for division. On the other hand, when I'm adding or subtracting, the number of decimal places in the answer equals the number of decimal places of the original number with the lowest number of decimal places. So if I'm taking a number with 3 decimal places and I'm adding it to a number with 1 decimal place, my answer has 1 decimal place. And the same goes for subtraction. Let's try some of these. So how many significant digits are there in these numbers? Well, the left-handmost non-zero digit is always the most significant. And in this case, there is not a decimal point. So I go to the right-handmost non-zero digit. And all the ones in between count, so that gives me 2. Not 4, because there's no decimal point. In this case, my left-handmost non-zero digit is the most significant, and now there is a decimal point, so my right-handmost digit, even if it's a 0, counts, and this would be 6 decimal places. This one, right-handmost, there is a decimal point. Left-handmost, it's 2. Don't worry about the power. That makes no difference. It's just the way you write down the number. And this one here, left-handmost, and there is a decimal point, so that 0 counts, and that's 3. So we need to be able to specify the number of significant digits. And then let's do some multiplications. So I have 12.3 times 2.1, and actually I want to show you something, so I'm going to do this longhand. I'm going to go 6, 2 2s are 4, 2 1s are 2, and I'm going to go 3, 2, 1, and then of course I add those up, and I get 3, 8, I get 5, 2. And I know that 2 times 12 is 24, so there's my decimal point. Now let's think about this. That is an uncertain 3, and that's an uncertain 1. So in this first row, I multiplied a certain 2 by an uncertain 3. So that 6 must also be uncertain. And in the bottom row, I multiplied everything, the certain 1, the certain 2, and the uncertain 3, by a 1, but that 1 wasn't certain either, it was uncertain. So these 3 must also be uncertain. And I ask myself, how many uncertain figures can I have in a measured value? And the answer is 1. So I've got to modify this, and it's going to round actually to 26 meters squared. It's going to round to two significant figures, and because that's an 8, it's going to round up, so it's going to round to 26. Or I could just turn around and use the methodology, and I go, well, it's 25.82. Let's have a look. That's a 2 significant figure, that's a 3 significant figure. I'm multiplying, so I use significant figures, so I have to round this, so that goes to 26 meters squared. Either way, you end up with the same answer. You end up with 26 meters squared. So it's not mathematics, it's science. And then the last one here is going to be, let's have a look, it's going to be 72.4 added to 38.36. And if I add these together, I get a 6, and I get a 7, and I get a 10, and I get an 11. Okay, so that's going to be what my mathematics says. But now, again, if I use this significant figure idea, the uncertainty idea, then that 6 is uncertain and that 4 is uncertain, which means those two are both uncertain, and I'm only allowed one uncertain digit. So I get 110 point. Now with a 5, there's various rules. The rule I learned was you just alternate every time you do a 5. I'm going to round this up to an 8, and then I have my kilograms. The idea behind the 5 rule is that you don't always round up, or you don't never round up. You've got to divide it up as you go through a job. And then I could just use the rule, of course, and say, well, this is 110.75. Oh, it was a 6. I'm sorry, it was a 6. 0.76. And I can say, oh, I'm only allowed 1 decimal place because that's got 1 decimal place, because I am adding or subtracting. And therefore I've got to round this, so this would be 110.8. Don't forget your units, kilograms. Let's do another thing, which is the factor label technique. This is a way of changing units, for example. We all know how to do it. We use basically conversion factors. But the problem is sometimes we multiply by the numerical value and sometimes we divide. So this is a way of getting it right. And my old chemistry colleague, Mr. Nyan, taught me how to do this, and it saved me a whole bunch of time. So I'm very grateful. Because people try to do it in their head and they try to just do it on the fly, and they every now and then make a mistake, and this way you'll never make a mistake. So this question says convert 4 steps per tick, it's just an unusual thing, into meters per second if 3 steps equals 9 centimeters and 2 minutes equal 34 ticks. Okay, so I have 4 steps per tick, that's 4 steps for every 1 tick, and then I put a line down and I say, well, let's convert steps first. So steps was on top up here, so by mathematics steps must be put on the bottom down here, so they'll cancel. And if the steps is on the bottom, then centimeters must be on the top. And so I look at my conversion factor and I say 3 steps is 9 centimeters. And I've nicely got rid of my steps. Now I want to get rid of my tick, and so I put tick on the top so it will cancel. I want to cancel out this tick, and so I put tick on top, and I look at my conversion factor, and tick gets converted into minutes, so minutes must go on the bottom, and I know that 34 ticks equals 2 minutes, and I just cancelled out my tick. But I want it in meters per second, so I have to do an additional few steps. I'm in centimeters here. I want to get rid of centimeters. Centimeters is on top, so now I have to put centimeters on the bottom, so the centimeters will cancel. I know from my conversion in my head that 100 centimeters is 1 meter, so I've just got rid of my centimeters, converted to meters, and now I need to get rid of this minutes. Minutes is on the bottom down here, and I want to get rid of it. I want to put minutes on the top so that it will cancel. That means that the seconds has to go on the bottom, and I go 1 minute equals 60 seconds, and now I'm in meters per second, and I get my calculator out and I do my calculation, and I get 0.043 meters per second. I'm not worried here about significant digits. So you noticed I'm doing a calculation, so I'm not worried about significant digits because I multiplied and divided and I have a one significant figure here. And so my answer, according to significant figures, would be one significant figure. And it's not. I've run it on a bit. And the reason for that is we draw a distinction between when we're in the lab doing measurements and when we're in doing homework and practice. It's a calculation under those circumstances. Let's do another example. This is 3 pec per 1 dross. I deliberately make up these units because some calculators enable you to actually just plug in one set of units and it'll tell you the other. But by making up my own units, you can't do that. And I want to be in meters per second, so I look at pec and I go 1 meter equals 6 pec. Oh, so let's put pec on the bottom so it will cancel, and that gives me meters on top, and I know that 6 pec equals 1 meter from my conversion factor, and so I just got rid of pec. And now I'd like to get rid of this dross, and I see over here that 1 dross equals 5 seconds. Put dross on top and seconds on the bottom, and 1 dross equals 5 seconds. So then this gives me, let's get rid of our dross, cross it out. So that gives me 3 on top, 3 times 1 times 1, over 30 on the bottom, 6 times 5 times 1, and I can do that in my head, and that's going to be 0.1 meters per second. So my right answer is there. Cool. Final little bit. This is a little bit of a sidestep, but this is the end of this section. And I want to tell you a little anecdote. When I first came back to teaching after years in industry, and I was doing my homework in front of the class, I would sometimes get it wrong. Actually, at the beginning, I'd sometimes get it, I'd catch myself, but I would be inelegant in the way I did the homework. And I realized that I had to improve my style. Because I was nervous in front of the class, I was making more mistakes. So I realized I had to actually go back to the approach, getting the approach right. And with word problems, this is the approach. You have to form a picture of the physical situation in your mind's eye. If you're not visualizing, you're going to have a problem with the problems that we do. You need to draw a diagram. Yeah, you might not be a beautiful artist. You don't have to be. The more you practice, the better you will become. The problem is you might have 3 or 4 or 5 forces in a diagram, and you have to know which force to select and how to combine them. And you can't do that without a diagram. So if you're not drawing diagrams, you're at a tremendous disadvantage. You need to list every parameter that's a variable. So you read through the question and you say, well, there's a position and there's a time and there's an acceleration. You make a list of things. And you also remember to put down the unknown, and the unknown could be a displacement, whatever. And when you look at that combination of parameters, it tends to jog your memory about the equation to use. So you recall the equation that links the unknowns with all or some of the parameters. Sometimes a teacher might give you an extra parameter that might tell you the temperature just to mess you up. So you've got to link it with all or some of the parameters and write down the equation. Then you do actually what is not the most significant bit, which is you do the math. You know, all the science and the physics is up here. The math is essential, but it's not the beginning and end of the problem. And you get a result, and then the final thing you do is you check your answer. Does it make sense? Sometimes I'll see students and they've got an answer that does not make sense, and so they don't go back and recheck their answer. And if they looked, they knew the answer. In their brain, they knew the answer was not right. But they just weren't thinking about it. They were just writing down what the calculator said. When I went back and focused on this again, I found that I could answer more questions. We all make slips occasionally, but I could answer more questions without making a slip. And it did me the world of good. So now ask yourself this: when are you under pressure? When are you more likely to make slips that will cause problems? When are you more likely not to be able to recall a question because you're desperately trying to work things out? It's during a test. So this is me talking as your coach. If I was sat over your shoulder watching you do a test, this is the thing that I would keep reminding you of. It will make a big difference to your performance over a physics course. So there we have it. Thank you.